Well, hello, mathematicians, and welcome back to our channel. This is a review of cubes and cube roots. Well, you'll recall that at one point we said that the area of a square was length times width. So for the object in front of you, which is a square and defined as a square because it has side lengths that are equal, all right? And there's a mark that we make to show that all the side lengths are the same. In this case, we're going to call them side lengths of 6 centimeters. Okay, so if the definition of a square is that it's a rectangle with equal sides. So if I know one side, I know them all, right? And so if I'm trying to find area, then I'm going to multiply side by side or length times width. And in this case, we have area is 6 centimeters times 6 centimeters, which gives me 36 centimeters squared or 36 square centimeters. All right, so this is what you learned before, and we learned that 36 was a perfect square because a whole number multiplied by itself gives that product, right? So 36 is the product of two whole numbers multiplied by themselves. And we can also write it this way: 6 squared is the same as 36. All right. So we said, just to review some vocabulary, that 6 is the base. All right. And 2 is the exponent. And the exponent tells us how many times we're multiplying the base by itself. Very important that we're not multiplying 6 times 2, which would only give us 12, but rather 6 times 6, 6 times itself, which is going to give us the whole area of the surface of the square. Well, then we moved on to talking about cubes, and cubes are related. I'm going to go ahead and draw a cube here. Not as good as if I had a little tool to make a cube, but let's say that this is a cube, and the definition here would be that all the edge lengths are equal, right? For the entire figure, that all of these edge lengths are absolutely equal. And we said that that is going to be 6 centimeters. So when we're looking at a cube, we're talking about volume. And actually, let's do 4, just because it's easier for me to draw. Let's say this one is 4 centimeters edge on edge, all right? So I'm going to draw in these 4 centimeters here. So each side has 4, and you know what? Each unit going up also has 4 of these layers, okay? So let me just attach that, right? And if we did the, I'm sorry for disproportionality, but if we did the area for each one of these layers, we would find that we have a length times 4 and a width times 4. And we know that 4 times 4 is equal to 16. Okay, so for this first layer going around, we have 4 times 4, which gives us an area of 16 on the bottom layer. And then as we went around again and we said 4 times 4, that's going to give us another area of 16. And we're going to do that again. And so we have 4 for the length and 4 more for the width. And if you multiply that layer, you get 16. And if you multiply this layer on top, you're also going to get 16. So that you wind up, if you looked down on your figure and you could see through it very clearly, you would have a, if you count those, you would have an area of 16 for each one of these layers going down, right? So it's not enough then, if we're trying to figure out how many cubes, let me shade this, right? How many of these units here are in the entire figure? It's not enough to say, well, just length times width because you also have to account for this height, all right? So then volume becomes length times width times height, okay? Or in the case of a cube, edge cubed, right? So we're talking about side times side times side, taking into account not just the length and the width, but also the height. And this is what we call volume. So we can say in this case, it is 4 times 4 times 4, or 4 cubed, right? So, and the way we write it is, as you see, the base of 4 and the exponent of 3. So this is 4 times itself 3 times, right? So it's not 4 times 3, which would be 12, but 4 times 4 times 4. And 4 times 4 is 16. 16 times 4 is 64. So if you were to assemble one of these cubes yourself, and I encourage you to do so if you don't believe me, you would find that it would take 64 cubes in order to assemble this particular structure with edge lengths of 4. All right. So 64 then is the perfect cube of 4. Just like 36 was the perfect square of 6. We call this a perfect cube. All right, let's move along. If we were to go ahead and then try and factor 64 to prove whether or not this is so, it would look something like this. 2 times 32 is 64. And 2 times 2 times 16 is 64. And 2 times 2 times 2 times 8 is 64. And 2 times 2 times 2 times 2 times 4 is 64. And you see where this is going. We're just going to finish this off. 2 times 2 times 2 times 2 times 2 times 2. Awful lot of 2's here. So if we rewrite this, 64 is the product of 2 times 2 times 2 times, eight twos, right? Or 6 twos, right, in a row. Now, we said before that 64 is a perfect square of 8 times 8. It is also a perfect cube of 4. So we're looking for 3 sets of factors that when multiplied will equal 64, and they've got to be identical. So in this case, we have 2 times 2 is 4, 2 times 2 is 4, 2 times 2 is 4. And you see those 3 sets of factors here, okay? So whenever you do the prime factorization, you're looking for a triplet, basically. 3 of exactly the same factors that can multiply to give us that number. And we can write this a couple of ways. We can say 64 is the same as 2 times 2 cubed. 2 times 2 cubed. We can also say it's 4 cubed. And we can also say that the cube root of 64 is 4. All right? So cube root is the opposite of cubing, right? So we write this like this. If you'll remember, square root had the radical sign and no number in the corner. For a cube root, we put a 3 there to indicate that we are going to take the cube root instead of the square root, all right? So if you see the radical sign here with a 3, that means that it wants the cube root. So the cube root of 64 is 4, and that's how we write it. The square root of 64 is 8, right? Because 8 times 8 is 64. So this happens to be a unique number that is not just a perfect square, but also a perfect cube. All right, so how do you find cube root of very large numbers? Suppose you had something like, this was one of your problems. We had the cube root of 1,331. Well, prime factorization is going to help you And I have taught you always to ask yourself, is it even? And if it's even, we're going to start with a 2. Well, in this case, it's not even, it's odd. So if we started with a 3, though, actually I can't divide that by 3. I know that it won't divide by a 5 because it doesn't end in a 0 or a 5, and it's not got a 7 in it. So the next prime number is 11, all right? And so I'm going to factor 11, and I get 11 times 121 gives me 1,331, and I know that 121 is 11 times 11. So there you see I've got 3 identical factors that I can use. So the cube root of 1,331 is 11. Now, it's difficult when you see these large numbers that are odd, right? Because you're not really sure, and you've got to do some work to figure out what can evenly divide them. Okay, here's another one. We have this enormous 6,859, and guess what? It looks like 3 should go into it, but it doesn't. It's not even, so I can't use 2. My next odd number is 5. It doesn't end in a 0 or a 5. 7 would be next, and nope, it doesn't work for 7. It doesn't work for 11. It doesn't work for 13. It doesn't work for 17. Actually, the next number that's prime that I can divide it by is 19. Okay, so you would have to do quite a bit of work to get up there to see that none of those prime numbers work until 19, right? And 19 times 361 gives you 6,859. And 361 happens to be 19 times 19. So the cube root of 6,859 is 19. Now, those are 2 examples where you're talking about quite large prime numbers cubing in order to make them. But the general way that we find out cube root is to go ahead and use this prime factorization. And certainly when you see a number like this, 2,744, and we're going to start with a prime factor of 2 because it is an even number, and I know that I can do that. So it's 2 times 1,372, and I can keep on prime factoring it. That's 2 times 686. And I have 2 times 343. And that looks familiar to me. I remember this. It actually is not divisible by 3. And I can tell that right away because I know that 300 is divisible by 3. It goes in 100 times. And I know 43 is not divisible by 3 because 42 is a factor of 3. So 3 is out. 5 is out, and the next one is 7. And it just happens that 7 times 49 gives me 343, and 49 is 7 times 7. Okay, so you see here with the prime factors that we have 3 2s and 3 7s. And by rewriting those, okay, I'm going to go ahead. We have to have 3 equal factor pairs or sets. I know there are 3 2s. And I see there are 3 7s. Right. So this would be 2 times 7 is 14. So I know that 2,744 is 14 cubed. So the cube root of 2,744 would be the same as the cube root of 14 cubed, right? And that is going to be 14. All right. So we don't have to do any more once we get to the bottom of the prime factors, and we see that we have 3 equal groups of the same factor pairs. And once we have those equal groups in front of our eyes, then we are good to go. All right, there was another problem in our homework that I thought was an interesting one, and it was to resolve this expression. And I want to remind you that the order of operations that all mathematicians agree on is parentheses, exponents, then multiplication and division. Multiplication and division will occur together. If you have a division sign first, you'll do the division sign. If you have a multiplication sign first, you'll do that. It's multiplication or division from left to the right in the order that it occurs. And then it's going to be addition and subtraction that are also buddies, and they will also be done in the order that they occur. So no parentheses here, but we do have an exponent. Here's our exponent. It's 9 cubed. All right, and 9 cubed happens to be 9 times 9 times 9. So that would be 81 times 9, which is 729. And now that we see that there's a 729 and we see this is, wow, I've got the cube root of 729 plus 729. And this just solved for me by doing this. I just solved for myself. Wow. I know what the cube root of 729 is. It's 9. So the answer to this expression, or the solving or reducing of this expression, gives me 738. All right. You do your exponents first. That was the first thing that happened. And then the only thing in here to do was to add. And, well, I had to resolve the cube root first, and then I could add. All right. One more kind of tough problem that I want to do with you. Okay. We have, and this is in number 20 on page 12 in your homework book, right? So the volume of a cube is 729 cubic inches. What's the area of each face of the cube? Well, the first thing I asked myself whenever I do one of these is to say, what do I know? Well, what I know is that volume is 729 cubic inches, right? And so I'm trying to find area. And I know that area is length times width. And volume is length times width times height. So if I find the edge of one of these edges, I can find the area, right? Because they're related. So I need to find the edge. And then this is my plan. I'm going to find the edge. And then I'll find the area, right? So I should be able to tell that the cube root of 729 will be the edge, right? And I know that 729 is 9 cubed. So the edge is 9, right? So to find area, then I'm going to do 9 times 9. and that's 81 inches squared. All right. I think that does it for our little review of cubes and cube roots. You know that they're the inverse of each other, that a perfect cube is a number that a whole number multiplies by itself 3 times. You know that an exponent must be, it tells you how many times you're going to multiply the base by itself. And you know how to factor very large numbers by asking yourself about the next prime number that you can factor out of it. And sometimes you have to go very high in order to get them. But that's about all you need, I think, to take away from this in order to do what you've got to do. So we'll see you next time. Bye.